Welcome to Lab 4, Part 3, Confidence Intervals. We're going to take on exercise 4.12 or 412 in this particular part of the lab. But before we do that, we should do a quick review of what the central limit theorem says and one more time about how we create a confidence interval. So to do that, we'll go ahead and get the whiteboard open here. And so start off, first of all, with just a review of what the CLT says. The CLT is the central limit theorem. And what the central limit theorem is all about, it tells us what happens in particular with the sampling distribution of x bar. So the CLT is in many ways, for us at least, is talking about the sampling distribution of the mean. So what do we mean by a sampling distribution again? Well, a sampling distribution means what is the distribution of a statistic? If we're looking at our particular statistic, x bar, what is its distribution? In other words, if I come into any old stinking population of any old shape, let's say our population looks, skewed right, and I come in and I take a sample from this particular population. And let's say in this particular case that our sample size is greater than 30. That's one of the key things that the central limit theorem tells us, that if we provided that our sample size is greater than 30, if we take that sample and then we feed it, drop it into this machine here, this is the input here, dropping in, and this machine is called, x bar, and then the output from that is a sample mean. Well, what do we know about that sample mean? Well, that sample mean belongs to a new distribution. It's the distribution of sample means. In other words, we have a sample mean equal to an x bar, okay? Now, what was its job? Well, let's come back over here to our population model here. In our population model, we know that it had mean mu, and it had with it some associated standard deviation sigma. So this population has a population mean equal to mu, and it has a population standard deviation equal to sigma. In other words, those are based on having every last element of the population used in the calculation of these numbers. Okay, now we know that in reality that's pretty much not going to happen, that we're always going to have to sample in the real world, and so we're not going to have the true population mean. We're going to have a sample value of the mean, and it's going to be a point estimate. And what we'd like to know is, how good of a job did our point estimate do? Well, one of the big tools that we'll need is the fact that the distribution of the x bars taken from this population will also have a known distribution to them. It will be known that those values will be approximately normal. They will be bell-shaped. And this distribution down here is not the population distribution. This is the sample distribution. This distribution down here will have the same mean as the original distribution. That is, the mean of the x bars is going to be equal to the mean of the population. So again, let me do a little color coding here. Try and help us out here. These two are the same, all right? So the mean that came from the population is the same as the mean of the x bars. The standard deviation of the x bars, we'll call that sigma sub x bar. That's going to be equal to sigma divided by the square root of n, where, in this case, this sigma right here is the same as this sigma right here. Those are the population parameters, okay? Now, key things written down in English are that this, well, okay, first symbolics, then we'll go English, is that the model of the sampling distribution is going to be approximately normal, depending on the sample size. It gets closer and closer to normal the bigger the sample is, with mean mu and standard deviation of sigma divided by the square root of n, again, where that's mu and sigma from the original population we were sampling from. Okay, so if the sample size, put this in English and not in a picture this time, is greater than 30, lots of abbreviations of course, but this is comp book worthy. I want this in my reference book, all about what the CLT is. Then the sampling distribution of x bar will be approximately normal. And what we're going to know about it is that it'll have mean mu and standard deviation sigma divided by the square root of n. Okay, so you should write this in your reference book. This is an important little ditty right here, okay? All right, cool. So that was a great little review of the central limit theorem. Let's go take a look at exercise 4.12 now. So I've already typed this up, or actually transferred it over into an R markdown file, and it's on Thanksgiving shopping part 1. So a quick commentary real fast on the knitting of this file for when you get done. One of the things that you want to do, I've kind of come back and cleaned mine up a little bit since probably looked at it last, is it to know that in order to get spaces between your problems, you need to put a line space in, and you need to end the previous line with a double space. In other words, when you end a line, if you want to put a line break in an R markup file, you put a double space at the end of that, and then you hit a return, and it'll break the line for you. So, for example, here I found a typo here while I'm looking at it. If I want to put in this sentence, line 14, to be separate from line A, if I put a double space at the end, that'll definitely make it so it moves down there. Okay, anyway, just point that out to you. All right, anyway, let's get on to this problem. So 4.12, Thanksgiving spending, part 1. The 2009 holiday retail season, which kicked off on November 27, 2009, the day after Thanksgiving, had been marked by somewhat lower self-reported consumer spending than was seen during a compatible period in 2008. To get an estimate of consumer spending, 436 randomly selected American adults were surveyed. Daily consumer spending for the 6-day period after Thanksgiving, spanning Black Friday weekend and Cyber Monday, averaged $84.71. A 95% confidence interval based on the sample is $80.31 to $89.11. Determine which of the following statements are true and false and explain your reasoning. Okay? All right, so notice that they said 436 randomly sampled adults surveyed. So it doesn't matter whether or not the distribution of spending was skewed left, skewed right, or anything, because the sample size is large enough. So let's go back for just a moment to our whiteboard area here. Actually, take a look. There is a picture. The picture from the textbook is right here. And notice that if we were to draw a smooth curve over the top of this distribution, it looks like the distribution of spending the week after Thanksgiving is skewed right, okay? But notice we came in and we took a sample here of N. Let me clean that up just a smidge there. Our N here was, what, 436, wasn't it, right? Let's go back and take a look at this so I remind myself here real quick here. And yes, indeed, we see it is 436, okay? All right, so, needle pulling thread here. The thing that we just reviewed was the central limit theorem, and it said, hey, if n was greater than 30, which by Jove it is, then the central limit theorem kicks in, and it doesn't matter at all what the shape of the original parent distribution is. The sampling distribution of x bar will be approximately normally distributed. So we can assume that in fact, it's a very safe assumption that that is in fact true, okay? That the sampling distribution of x bar will be approximately normal, and then the confidence interval process that we use, which is based in much upon the 68, 95, 99.7 rule, is in fact going to work, okay? All right, let's get back to our studio here, and let's go read the actual questions. All right, so question 1, we are 95% confident that the average spending of these 436 American adults is between $80.31 and $89.11. Okay, so pause this for just a second and take a stab at answering that. Write your answer down before you listen to the results. See what you think. Okay, so we're back. So what do you think? Did you come up with true or false? Well, notice that it's false. Why is it false? Well, because what they're talking about here is just the 436. And that's not what the confidence interval is about. The confidence interval is about making an estimate for the population. So a confidence interval estimates the parameter for the population, not just for the sample size. That doesn't make any sense actually, because we don't need a confidence interval if we just want to know what the average of the sample was. We will know what that is. That's X bar, okay? So a confidence interval estimates the parameter, if I could spell the word the, that would be such a nice thing in my life, for the population, not the sample. Okay. All right, let's play the same game again down here in part B. The confidence interval is not valid since the distribution of the spending in the sample is right skewed. So take a second, write that down. Write down what your answer is. You can pause this. Okay, we're back. What did you come up with? Hopefully, again, you said false here. And the reason being is no. Well, let's get rid of the word no. The CLT works here since the sample size is greater than 30. Hence, the shape of the distribution sampled from which is why we take big samples, because this works. All right. Okay, so since the sample size is greater than 30, the shape of the distribution sampled from, I should put a sampled from there, sorry about that, doesn't change the result. Okay, in other words, it doesn't matter if it was skewed left, skewed right, bimodal, uniform, etc. All right. Okay, part C. Part C, take a stab at answering this one. 95% of such random samples would have a sample mean between $80.31 and $89.11. Okay, well, hopefully you got false on that one. This one's a little bit of a tricky bugger, but here's the thing to look at. 95% of such random samples would have a sample mean between $80.31 and $89.11. Well, think about that for a second. Every time you generated a new confidence interval, you're going to get a new sample mean, right? And it's that confidence interval is going to be shifted one direction or the other. It's not talking at all about the sample mean. It's talking about the population mean. In other words, what a confidence interval tells you is it tells you how confident you are of having captured the population mean. It's not how confident you were about capturing the sample mean. So a confidence interval, or a CI, tells us about the population mean, not the sample. The correct version would be that we are 95% confident that the population mean is in the interval. Okay, all right, so a little bit of a tricky dog there, but hopefully you understand that one. Let's go take a look at part D here. We are 95% confident that the average spending of all American adults is between $80.31 and $89.11. Got your answer? Ready to go? Okay, so this one is true. If I only got a true one. That's so negative there, so false. This is the definition of a confidence interval. In many ways. I mean, there's more to it than that, obviously, but this is basically the golden sentence that we want to know. So we are blank confident that the average spending, of all Americans, or you could shorten this to say the population average, is between blank and blank. So this sentence right here, you want to take a look at that one. That one should be in your comp book as boilerplate for whenever you answer a question about a confidence interval. Remember, as we talked about in the last video, there's not a 95% probability that the average spending of all Americans is between 80.31 and 89.11. Confidence is not the probability that the parameter is in the interval. Confidence is the probability that our process worked. That's why we don't say there's a 95% probability that the average spending of all American adults is between 80.31 and 89.11. That would be wrong. Confidence has a very specific definition. It's the probability that the process that we used to create the interval worked in capturing the interval. I know that seems rather nuanced. It takes a bit to get your brain wrapped around it. And when I first learned it, it definitely took me some time to figure out the difference. So yeah, make sure you got that sentence for the time being until your brain gets wrapped around it. Okay, part E, a 90% confidence interval would be narrower than a 95% confidence interval since we don't need to be sure about capturing the parameter. I'm not going to torture this one. This one's kind of badly written question, but we need to do it. What they really meant here to say is that the 90% confidence interval, yes, it is going to be narrower, but it's not because we don't need to be sure about capturing the parameter. It's narrower because Z star is going to be smaller. That's why your confidence interval is. So this one is false. Bad question. Let's just leave it at that, okay? All right, in order to decrease the margin of error of a 95% confidence interval to a third of what it is now, we need to use a sample 3 times larger. Okay, well, what do you think about that one, true or false? Give you a hint. Think about the standard error and what's in the denominator of the standard error. Okay, this one again is false. Why is this one false? We would need to take a sample size 9 times larger. Now, why would we need to take a sample size 9 times larger? Well, what's in the denominator of the standard error? It's the square root of n, right? And what's the square root of n? It's 3. So if we wanted it to be a third, in other words, if we wanted that square 1 over the square root of n to end up to being a third, we would have to take a sample 9 times larger in order to make that work. Okay, think about that for a minute. Just do paper and pencil and try that. Okay, last but not least, the margin of error for the reported interval is 4.4. All right, that one, let's go ahead and work that one together on the whiteboard. It turns out that one's true, but I think to see that one would be handy to have gone through it on the whiteboard. So let's go ahead and get ourselves a clean whiteboard here. I thought I had several built, but I guess I only got one. That's all right. So let's think about how do you actually build a confidence interval, and let's do it with respect to this particular problem. And so the best way to think about it is looking at a number line. And what we have in this number line is 2 numbers. We have our beginning of our confidence interval and the ending of our confidence interval. So this is the $80.31. That's the lower limit of our confidence interval. And we have the $89.11 up here in the upper interval. Now, what we know is the center of this interval is going to be at x bar. Now, they gave us in the problem, they told us what the center of it was. Let's go back for just a moment here to remind ourselves. If we go back and look at the document, remember they told us back up here that of the 436, that it was $84.71 was the average, right, of our 436. So 84.71 is going to be equal to our mean. All right, so how was the confidence interval created? How did we get this 89.11 and how did we get this 80.31? In other words, where did those numbers come from? Well, if you recall that the general idea behind a confidence interval is you take your point estimate, in other words, what is the estimate of your parameter, and then you add and subtract from that your margin of error. Well, how do we calculate the margin of error in this particular case? Well, since we're talking about the sampling distribution of x bar, since we're creating a confidence interval for the mean, we know that the margin of error, which many times is abbreviated just capital E, I'm going to go ahead and use that. So the margin of error is going to be equal to capital E here for our particular case. And so what is capital E equal to? Well, it's equal to sigma divided by the square root of n. That's our standard error. Whoops, hang on a second. I need to put the z star out front. It's going to look funny to you. So let me erase this real quick. I want to keep it in the order that we have learned it. Changing order on there would just be not a very good idea. Okay, so it's going to be equal to our z star times the standard error, which is given by sigma over the square root of n, right? Well, so in our case, what we're going to have to do is approximate that with our z star times s divided by the square root of n, okay? Now that's just review. We don't really need that to answer the question here, but it's important that you understand that that's what they mean by the margin of error. It's that piece right there, okay? It's that chunk that we add to it. In other words, a 95% confidence interval for the mean can be created using x bar, which is our point estimate. Let's do a little color here. So that's the point estimate right there, plus or minus the margin of error. Let's go ahead and do the margin of error in some sort of bluish color here. And the margin of error in our particular case is going to be given by z star times s over the square root of n, okay? Sehr gut. All right, now, as a matter of fact, we don't need to really use this formula to calculate it. We just need to do a little bit of arithmetic. Notice that what they're looking for is they want to know, let's do it in the same color, blue here, they want to know this distance right here, because notice that that distance is the margin of error. In other words, this endpoint, 89.11 here, is equal to x bar plus the margin of error. And this endpoint down here is equal to what? Well, that's x bar minus the margin of error, isn't it? So how do I calculate that distance right there? Got any ideas? Well, how about we take and find what? The total distance between the two endpoints and divide that by 2. In other words, if I know the length of my interval, if I know how long this distance is between here to here, right? If I know that total distance, then I should be able, by cutting it half, I should be able to figure out what E is, because E is going to be this distance right here. So we know that the margin of error, E, is going to be equal to 89.11 plus 80.31, excuse me, not plus, my bad, excuse me. I want to know their distance. I'm not going to add them if I'm trying to find their distance. That's a subtraction there. Divided by what? 2. In other words, give me the distance, the total distance from here to here. In other words, I want that total distance right there, and I cut that in half, and I'll get the blue distance, which is my margin of error. Okay, so if I do that, go ahead and do that calculation, you'll come up with that is equal to 4.4. So yes, they were telling us the truth. They didn't lie to us in the last one. And as a matter of fact, that is the margin of error, okay? All right, so let's go back to our markdown file here. And let's go ahead and put in there and say, yes, this is true. And you could just put in the calculation there. You can just type it in. You can say, okay, so 89, parentheses, 89.11. In fact, if you wanted to put this into a chunk, you're welcome to do that. It's such simple arithmetic, though. It's up to you if you just want to do it, on your calculator or even in your head. That's fine. All right, okay, so that was a fair amount of stuff. You might want to make sure you watch this one again and check your reference book and make sure that you have all of the highlights that I mentioned in your reference book, and be sure and post any questions you have about this stuff to discussions.